Choudhary, and by profession, I'm a data scientist and AI enthusiast, but more importantly, a builder by the experience. For over the last 2 decades, I have been deep in the trenches of data, battling on-prem legacy bottlenecks to navigating the cloud migrations, implementing AI systems across different industries, and now exploring how quantum entanglement and photonics can unlock the dimensions of computations we have only dreamed of. If you have ever struggled to get faster insights from your data, or if you have watched AI models plateau due to compute constraints, this talk definitely is for you. I'm going to walk through the real world quantum algorithm, not just as a mathematical novelties, but as a game changer, as a game changing tools of it for in problem solving, optimization, and innovations. Will be a little technical, yes, but it will also be human because behind every algorithm is a decision, and behind every decision is a mission. Let's decode that together. And by end of this session, you will definitely walk away with a foundational understanding of quantum computing, insights into the real world business cases, and clarity on where this field is headed to and how can you get a part. So now I little bit discuss about myself and a bit about me, and let's talk about what are you going to walk away with in this next 30 minutes. I'm not here to throw a kind of like a expertise jargon on you. My goal is to make sure that every person who is watching this, whether you are a researcher, you're a cloud architect or product leader, or just a quantum curious, walk away with something actionable and understandable. You will grasp how quantum computing truly differs from the classical systems and what makes quantum logic so powerful. We will break down Shor's algorithm, Grover's search, and near hybrid approaches, and you will actually see in the production today. And from drug discovery to fraud detection, I will share with where quantum is already being a pilot and where it's headed. Because yes, some of what you hear out there is hype, but a lot is real. We will distinguish fact from the fiction. So you don't need to be a quantum expert to get this. You just need to be curious and open. And if you are, I promise that you will leave this session 10 steps ahead of where you started. The greatest enemy of the knowledge is not ignorance. It is the illusion of knowledge. I love this quote from Stephen Hawking. And Stephen Hawking is not just about talking about the science. He was talking about human nature. We stop asking questions when we think we already know the answer. And that mindset has held back technology for decades. Most of us have grown up believing that all computers work the same way. They process ones and zeros, they follow instructions, and with more speed and memory, they solve the bigger problems. That model called non-Newman architecture, invented in 1940s, has taken us from floppy disks to the cloud computing, and it's the foundation of everything they use today. Your phone, your laptop, even iModels. But there is a catch. It has limits, and we have started to hit those limits now. And nature doesn't compute in ones and zeros. Nature is messy, probabilistic, non-linear. At the atomic level, their things are not just on and off. They exist in multiple states at once. They influence each other without touching, and they behave in ways that seems irrational but are deeply mathematical. So to stimulate the nature, to model a molecule or understand quantum physics or solve the certain optimization problems, we can't keep using classical logic that trying to paint the ocean with a pencil. In 2019, World's quantum processor, Sycamore, performed a computation called random circuit sampling. Is not just a useful problem, it is extremely hard for classical computers. Sycamore solved it in in a 200 seconds. IBM argued their classical supercomputer could have done in 2.5 days, but even that is a staggering difference. Whether it was 200 seconds or 2 days versus 10,000 years, the point is classical computing is not always the fastest tool. Sometimes it's not even the right tool as well. So its quantum computing does not replace the classical computers, it complements them by solving a new class of problems that rely on principles like superposition, entanglement, and interference. That's what we will explore today: what quantum algorithms are, why they matter, where they are being used, and how they will change everything from cryptography to the chemistry to AI. So let's first understand from the ground up what makes quantum computing different and why everyone from IBM to NASA to startups like Exendo in investing in this space. And let's start with a simple classical computer like a phone in your pocket or a server in the cloud is built on bits, right? Each bits hold a value, either 0 or 1, just two options, just like a light switch. So it's either on or off. This is the digital logic we have used since science. Every program, every video, every AI model made of billions of those switches flipping on and off really fast. But the quantum computers use qubits, which is quantum bits. And these behave very differently. Instead of just being 0 and 1, a qubit can be both at the same time. And this is called superposition. It's like a spinning coin, whether it's in the air or it's not head, not tails, but it's both. Only when you measure it does collapse into ones. Now imagine like you had two spinning coins in front of you, but they are somehow entangled, meaning whatever outcome you get, no one will instantly affect the others, no matter how far apart they are. Einstein called this spooky action at a distance, and this is the magic of entanglement. When you combine superposition and entanglement, you can represent and process many states at once. A classical bit gives you one calculation at a time, but in quantum bits, qubits can represent two possibilities at once. So that means 2 qubits, 4 states, 3 qubits, 8, and 10 qubits, already over 1,000. 300 qubits, more state at the atom in the universe. So now to be clear, this is not just magic. You still have to run a smart algorithm to extract the right answer. You don't just get all the answers for free. Quantum computing is not about doing everything faster. It's about doing certain problems differently. Problems like factoring massive numbers, simulating molecules, optimizing delivery routes, or training quantum enhanced AI models, where the solution space is so vast. Classical machines hit a wall. So classical computers is like walking through every hallway in a giant maze, one at a time. Quantum computing is like entering all the hallways at once, but using interference patterns to cancel out the wrong paths and amplify the right ones. The key concepts to remember are here in this specific slide is superposition. A qubit can be many things at once. In second is entanglements. Qubits can be linked beyond the space. And number 3 is interference, which is used to find useful answer from noise. So with these two, quantum computer don't just calculate, they explore. Now let's go to the next slide, which is a quantum advantage. Now that we understand what makes quantum computing different, the real question is whether or where does it matter? What problems actually solve better than the classical computer? The term we use is quantum advantage. It means that quantum computing solving problem faster or more efficiently than the best classic supercomputer ever can. So even with the unlimited time and the memory, there is not theoretical. In 2019, Google claimed the quantum advantage for the first time using a random circular sampling task. While the usefulness of the task was debated, the milestone was clear. For that specific problem, typical computers simply couldn't keep up. And let me break it down like simulation of those quantum systems. And nature itself is a quantum. So if you want to simulate an atoms, molecules, or materials using classical computers, is like translating poetry with a calculator. So quantum computers are built on the same physics. So they can actually naturally simulate chemical interactions, energy states, and the molecule bonding, things that require approximations on classical machines. This has a huge implications for drug discovery, material designs, and even the sustainable energy development. These shows up everywhere. Logistics, finance, traffic systems, and even for machine learning, hyperparameter tuning as well. Classical solvers like linear programming are heuristics are fast, but they often hit the local minimal or something that limit, not the best solution, just a nearby one. So quantum algorithms like the quantum approximate optimization algorithm, which is QAOA, exponentially more options in parallel and offering a global solution. Shor's algorithm is developed in 1994, is perhaps one of the most famous quantum algorithm. It can factor large numbers exponentially faster than the classical methods. And why does that matter? Because modern encryptions like RSA is based on the assumption that factoring is hard. If large-scale quantum machines becomes practical, encryption will break. This is why we now talk about post-quantum cryptography, which is already a top priority for the national security as well. And it's very important to clarify that quantum computer won't replace everything. It is not going to run your Excel spreadsheet faster or replace your phone's processor. It shines very specific domains, problems where the search engines grows exponentially or where quantum interference gives it a unique computational edge. Think about searching for a needle in a haystack. A classical computers check each straw one by one. A quantum computer uses Grover's algorithm to search the entire block or entire haystack in square root time, which means that problem with a million possibilities can be solved in about 1,000 steps instead of million. That's not just a speed, that is about, you can say, new kind of a like formula. Quantum advantage is not universal, but it is a profound when applied to the right kinds of problems. Simulation, optimization, and cryptography, quantum computer don't just offer performance boost, they offer is the only feasible path forward. Now I will walk you through quantum computing didn't just appear overnight. It's a product of the decades of theory, physics, and engineering. Many of them are initially dismissed as impossible or just math, but here we are. Just a little bit of our history. In 1981, this all started from a physicist, Richard Feynman, who asked a simple question in 1981: why can't we simulate physics on a computer? His answer: because computers are not built on the law of physics, but if we could build a computer that behaves quantum mechanically, it could simulate nature itself. And this was the seed, and it launched a whole new field. Then came the major shockwave in 1994. Peter Shor at Bell Labs created an algorithm that could factor the large number of exponentially faster than any classical algorithm. And this was not just a math breakthrough. It was a direct threat to the security of the internet. Suddenly, quantum computing became not only a curiosity, but a strategic priority as well. Then Love Grover at Bell Labs developed an algorithm that could search unsorted databases in square root time. This may not sound dramatic, but in the computer science, going from ON to the O square root N is huge, especially when N is in the billions. So truly the field shifted from the theory to hardware. IBM, Intel, and startups like D-Wave began building actual quantum chips. But they were like skeptics. Like the main challenge was qubits are fragile. They decode easily. Even a breeze of temperature or vibration can corrupt them. So in 2019, Google's team published a paper claiming that they have achieved quantum supremacy, meaning that their quantum processors solved a problem that was practically impossible for a classic computer. While use case for narrow random circuit sampling. The industry milestone was massive. It validated the decades of the work. So in less than 40 years, we have gone from chalkboard theories to functional computers processes, and that's lightning speed compared to the history of the classical computer. But remember, we are still early. We are in the NISQ era, where it's called noisy intermediate scale quantum. The chip exists, but they are error prone and still the pace is accelerating really fast. Now that we know about the quantum computing came from, let's look at the algorithms that are turning this theory into the real world impact. And let's look at a few quantum algorithms, the ones, so you have seen how many algorithms. One is we have already discussed. One is the Shor's algorithm in 1994. This one cracked the world open. Shor's algorithm factors the large integers exponentially faster than the classical computer. And why care? Because that's how RSA encryption works, the backbone of the internet security. And if quantum computer with enough stable qubits exists, it would break RSA to 2048 in a days, while classical computers would take millions of years. So that's why governments are now investing in post-quantum encryption. The 1996 Grover's algorithm searched a unsolved database. It's like skewer n times instead of n. That's a quadratic speed up. There was like quadratic speed up, and in the fields like machine learning or bioinformatics, this can save a number of years in computation. Quantum approximate optimization algorithm, QAOA, is a hybrid algorithm explain the classical and quantum processing. Wait for the real world optimization tasks like delivery, routing, and network balancing, and even the financial modeling as well. Vibration quantum, which is VQE, is used in the quantum chemistry. It estimates the ground state or energy of the molecules. That means faster drug designs, material innovation, and even sustainable energy discovery. So there are not sci-fi ideas. They are already being tested on IBM, IonQ, Exendo, and others. Quantum algorithm won't replace classical one at all, but they will just unlock what classical code cannot reach. Use cases, that how is quantum computing being used right now. Let's look at some few sectors that are not just experimenting, but they are investing as well. One of the companies like pharmaceutical company Roche and AstraZeneca are partnering with the quantum startups to simulate molecules and predict protein folding, something classical computer can do at scale. Quantum help identify viable drug candidates faster, potential say billions in R&D and speeding up the time to market. In finance industry, firms like Goldman Sachs and JP Morgan Chase are exploring quantum for optimizing the assets portfolios and running Monte Carlo simulation more efficiently. These problems have exponential complexity. Quantum algorithms offer a better way to explore risk scenarios. In logistics and supply chain, Volkswagen and DHL are testing quantum systems for traffic flow optimization and route planning, especially where classical computer or classical systems get overwhelmed by too many variables. Where even 1 minute of save time per vehicle can scale into millions in the savings. In energy sector, ExxonMobil and BASF exploring the quantum chemistry to discover better catalysts for cleaner fuel production and energy storage. It can simulate chemical reactions that would take classical supercomputers centuries to approximate. Quantum computing is already used in narrow, high-impact tasks, not to run your website, but to reshape definitely R&D, your supply chain, and your competitive edge. Most of the quantum computers used today superconducting qubits. They're tiny electrical circuits cooled to near absolute zero. But there is another approach gaining traction is called photonic quantum computing. So instead of electrons or ions, it uses photons. There is a kind of like particles of light to represent the qubits. Photons are naturally quantum. They do not interact with their environment easily, which means they are less prone to noise or any kind of like decoherence. One of the biggest challenge in quantum hardware is like unlike superconducting qubits, photonics can operate at room temperature and use existing fiber optic infrastructure as well, and the same tech in our internet cables. So companies like Xanadu in Canada and PSI Quantum, which is in the US and UK, are building the full-scale quantum processor based on the photonics. Xandu's Borealis system was the first photonic quantum computer to demonstrate the sampling at the scale. And this is very specific, very hard problem, but it proved that photonic chip can are not just theoretical, but it's extremely practical as well. But it still faces some challenges. Generating and manipulating single photons reliably is really tough. And building logic gates using light alone is not as mature as superconducting tech today here. So if we crack scalable photonic quantum, we get faster, cheaper, and most robust quantum systems. And we can build them using the same optical components already mass produced today. And now let's talk about what quantum computing can do yet, because we are still very early in innings of this field. Qubits are very fragile. They lose their quantum state within microseconds. This is called decoherence. So even the tiniest heat or the vibration can throw them off. This is why quantum error correction is one of the biggest bottlenecks. To get one reliable logical qubit, you might need hundreds or even thousands of the physical qubits. Today, quantum computers are called some of the devices, which is noise and fault tolerance is NISQ devices, noisy intermediate scale quantum. They are not fully fault tolerance yet. You can run small experiments, but scaling them is still a hurdle. Superconducting systems can need extreme cooling, it's needed trapped ions, lasers, photonic chips, needs precise light control. And all these platforms have strengths, but no one has solved the scale challenge yet. So most quantum algorithms today are still exploratory, but for many real world problems, we haven't yet proven a quantum solution that is truly better than the classical. There is also a hype bubble. Some companies make quantum solutions that are not quantum at all. As researchers and builders, we have to separate the science from the PR. So yes, the potential is massive, but we are not there yet. We are not in the ChatGPT moment of quantum computing. This is a deep tech field. It's not just a finished product, and that's okay. It's the internet took decades as well to come into the production. So now we have to talk about where we are today now. So where exactly are we on quantum roadmap? The answer is early but accelerating fast. We are in NISQ era, which is a noisy intermediate scale quantum. This means that we have real machines, but they are noisy, limited in the scale, and not for torrents yet. So not enough for full cryptographic breakthroughs, but enough for the experimentation, hybrid models, and early optimization trials. There was a commercial pilots live. Big pharma like the pharma finance and logistics are running parallel or limited pilots to test real world viability. And then we are probably 5 to 10 years from full scales for Torrance quantum system. But if you wait until then to start, you will be too late in this race. Now the quantum hardware landscape. Let's quickly talk about what's under the hood, because not all the quantum computers are built the same. There are four main types of the quantum hardware platform. Number one is superconducting qubits, which is used by IBM, Google. They are fast but need extreme cooling. Good for the near term, you can say experiment. Then we have a second type is a trapped ion, which is used by IonQ and Honeywell, more stable and precise but slower gate speeds. Then we have photonic quantum computers like Exandro, APSI Quantum. It's leverage the light, room temperature, great long-term scalability. Then we have neutral atoms and topological qubits used by QRA and Microsoft. Still early stage, but promising for error resistance. So the race is not just over. We just don't know which architecture will win, but the diversity of the approaches is what makes this space so dynamic. Here is what I will just let me discuss about the where is still heading the next 5 to 10 years. Let's break it down. So by 25, 22, 28, and then SQ maturity is that more stable qubits, hybrid quantum, classical models become common in R&D environments. From 2028 to 2023, 32 error-corrected quantum computers, we will likely see the first 1,000 plus large qubit system capable of beating classical in real production. integration, and post 2032 quantum integration into cloud ecosystem, which will be like quantum will become a service embedded into AI and analytical stacks, and you will call it from an API or like any other tool. So we are moving from lab experimenting to infrastructure grade tools like AI. The winner won't just be like those who build the tech, but those who learn how to apply it early. You don't need a PhD in physics to start building quantum application today. These are tools. Many are free and let you experiment right now in the cloud as well. One is what I personally use as well is IBM, which is a Python based open source and backed with a real hardware on the IBM cloud. IBM Quantum Cloud. And then we have a Google CIRQ, great for the NISQ algorithms, especially the quantum circuits. Microsoft Q Hash and Azure Quantum, which is built for the hybrid quantum classical workflows. Then we have a Amazon Bracket native is connected to the multiple hardware brackets. IonQ, Rayjet at Oxford. And then we have a Exander spanning lane, which is focused on the quantum machine learning, integrates well with the PyTorch and the TensorFlow. And whether that you're a data scientist, developer, or just curious, you can access the real quantum hardware from your laptop today. And I will say here's what I want to walk away with today in three clear takeaways. Quantum is not magic. It's a math plus physics and engineering and a blend of AI, but it changes what's possible. Problems we thought unsolvable are now being modeled. We are still early, but not too early. You don't have to wait for perfection to get involved. The learning curve has already begun. The future will be hybrid, classical and quantum, AI and physics, code and light. And those who cannot connect those words would definitely need now to start work on that, because if you connect these all doors together today, that you will definitely there is high chances of leading. And if there is a one thing that I hope this talk did is I hope that this give you clarity, not confusion, and curiosity, not fear, and most importantly, a reason to explore as well. Thank you so much for your time and your patience, and thank you all for being here. Truly, I know this is a complex topic, but the fact that you showed up tell me that you are not afraid of the complexity. You are here to lead the future, not just wait for it. So if today sparked any kind of ideas, a question, or even doubts, let's stay connected. I share a lot on LinkedIn, and I love talking shop, whether it's quantum AI, data architecture, cryptocurrency, or blockchain, or wherever is converging. So you can find me under Sarah Choudhary or reach me out directly as well from the LinkedIn messages. And you can check me on Linktree/Sarah Choudhary. Quantum computing is not just about faster answers. It's about asking the deeper questions. And that's where the transformation begins. Thank you very much.